All right, our next speaker is Michael Castelle from the University of Warwick, who's going to be speaking about our neural networks, neoclassical, utility loss, and the cost from Wald to TensorFlow.
Thank you. All right, this is the title of my talk. I would like to start just by making a sort of a nod towards a past critical AI and a sort of hope for a future 21st century critical AI with Dreyfus and Lucy Suchman and Phil Eger. Phil Eger wrote about the need for a critical technical practice for which critical reflection upon the practice is part of the practice itself. If we have mistaken ideas about human nature, they'll lead to technical challenges. And this is also true for AI projects that use ideas about human beings as a heuristic resource. So this is trying to sort of piece together a history of how that plays out in contemporary deep learning. So this is just a quick outline to see deep learning as an epistemic ensemble, to look at their distinctive features. I'm going to focus on the loss function. I'm going to talk about the origin of loss function in statistical decision theory, and talk about how that developed in 20th century economics, and then sort of try to figure out what might be the sort of underlying economic ideologies of contemporary deep learning practice. So this is just a way that I've sort of come to think about deep learning that isn't about it being a revolution and more about it being a kind of like a synthesis of past sort of knowledge regimes. It brings together aspects of behaviorism, like most notably in reinforcement learning, aspects of cognitivism, obviously connectionism. I would say that word embeddings are very structuralist. Levi-Strauss would have loved word embeddings, and algorithmic modeling, this sort of like Leo Breiman sort of view of machine learning is obviously a strong component as well. So this is another list. I'm not going to go through all of these because I'm focusing on the loss function, but it's important that to understand deep learning as being a very experimental, experiment-centric culture. It obviously is sort of focused on prediction. It's got layers, everything's vectorized, etc. These are all important, but today I'm just going to talk about this loss function. And so this is just a sort of way to think about it through this animation of a multi-layer perceptron trying to learn to classify handwritten digits. As you can see, if you can sort of watch on the side here, when it sees a 1, it classifies it as like a 0 or a 4 or something. And the backpropagation process sort of, is one which creates that loss surface and allows it to kind of explore the weight space in order to do better next time. And so the loss function is really just the value that causes this process to have the backpropagation process to happen. And so if you see people sort of doing contemporary AI, you might see them staring at these kind of diagrams. So on the left, you can sort of see that the blue training set, as you train, the value of the loss function gets lower, and the value of the loss function on the held out test set gets higher. That's bad. That's overfitting. And you want to see something that looks more like on the right, where the values of the loss function for the training and test data are both heading down. The definition of these loss functions can be very simple. So for multi-category classification, it's just like the negative log of the value of the true class that you think it is. So if it's a picture of a tiger and I think it's very close to 99% a tiger, then I get a very low loss score. If I think it's 1% a tiger, I get a high loss score, and that's bad, and my network will update. This is also very concise in the code itself. So if you're writing this stuff, you just sort of like you define your network, and then you can specify that the loss is categorical cross entropy, and you go on to train the model. But the reason I'm focusing on it is because I think it represents this kind of Achilles heel of deep learning models, that it's a possibility to sort of critique it from this angle. Because when I sort of started to think about it, and I hadn't heard of loss before, it seemed like a strange sort of category. It turns out to be introduced by this statistician, Wald, in 1949, and he described it as the loss function as a measure of the quote-unquote loss to the statistician if one takes a certain action when the true state is a given one. And I thought that was pretty interesting, because usually you wouldn't think of the loss to the statistician being something that's embodied in the data. It's embodied in the sort of social situation of the statistical analysis. So it's an interesting definition to explore. In this talk, I'm going to sort of show how that concept was picked up by economists and sort of brought into the world of their rational actor that maximizes the utility function. So if you sort of tune out now and you want to take one thing from this talk, it's that loss is equal to negative utility. If someone's talking about maximizing their utility, you're talking about minimizing your loss. So That's as simple as that. It's true. It's mathematically valid. Whatever. Okay. So here's a hagiography of Abraham Wald. He's a Hungarian Jew from Romania, and he sort of came to statistics through economics by a tutoring called Schlesinger. He escaped the Holocaust by being invited to the CALS Economic Commission in Colorado. He comes here to Columbia, writes a bunch of papers, joins the faculty, and also significantly works at the Statistics Research Group, which is right down the street, or was right down the street, and dies tragically in 1950. I want to talk about the Statistics Research Group briefly because it's nearby. It's down at 401 West 118th Street, and it had a lot of economists on it. It was a wartime research group that was focused on sort of economists and statistics at the same time. There are 30 computers from Hunter and Vassar. It focused on kind of like geometry of aerial combat and whether or not like your plane's getting hit by anti-aircraft, how to what angle to shoot a torpedo into the ocean, that sort of thing. But significantly, what came out of it is sequential analysis, which is primarily developed by Wald. It would have many applications in sort of wartime post-war quality control. There's a great article by Judy Klein, Economics for a Client, that I really recommend if you want to dive into this. Game theory is something that's happening at the same time and very appealing to this particular crowd, although not too appealing to anybody else at the time. If you're familiar with game theory, the gist is kind of that there's a set of rules that describe sort of formally the alternative moves available, in what situations the game ends, and what happens when the game ends. Specifically, what usually happens in the game is there's a payoff or a value assigned to each player. And the concept of a zero-sum game is one in which the payoffs to all the players add up to zero. So if I win, you lose, and if you lose, I win. Sorry. So Wald's paper on statistical decision functions basically sort of brings sort of the notions from game theory into sort of this nascent decision analysis. And so he talks about basically doing statistics as a zero-sum game, with the first player being nature and the second player being the statistician. So if I guess that the true values, the true parameters of nature are D, and the real parameters of nature are theta, then I can define a loss function that sort of describes like how badly I got it wrong and how much I should be punished. This gets picked up by economists in a kind of weird roundabout way, which is sort of the topic of this amazing Giaccoli article, From Wald to Savage. And so it's about how Homo economicus becomes a Bayesian statistician. It's a really crazy story because basically Jonnie Savage, who's another statistician at the research group, tries to sort of like take Wald's theory and apply it to all of sort of statistical practice, right? But ironically, it winds up being taken up by economists who then basically use the notions of this sort of perfect, pure, like Bayesian statistician and use that as the sort of formal model for the rational actor, the concept that's existed for a while, but sort of takes on a new form in the late 20th century. So it's a really great piece that kind of does a lot of work for me. If you want to understand sort of a little bit about what, how neoclassical economics changes, you can just sort of look at that row that talks about utility functions. So there's no reference, there's lots of reference to maximizing utility and marginal utility, but no concept of this kind of utility function. And then by 1971, it's like 100% of economics textbooks are talking about utility functions. So it's a pretty rapid shift. This sort of the standard critique, basically where I'm going with this is that the standard critiques of neoclassical economics can potentially be sort of unproblematically redeployed against contemporary AI technique. So the sort of components of it, I'm drawing from Moravsky here, is sort of a prominent neoclassical economics hater. He defines these main components as the use of this utility function, which again derives from Wald, the formal axiomatic definitions, and this methodological individualism. And his critiques of those are sort of like that, this use of a utility function means that learning is basically defined as unidimensional punishment of some kind. There's just a single value that tells you how bad you're being. There's no way to change your mind in this world. The axiomatic definitions means that it's hard to conceive of an actor behaving in different ways in different contexts, and it also denies the embodied and tacit and articulate and emotionally driven qualities of knowledge. And the methodological individualism, of course, denies the possibility of any kind of social cognition or social learning. While the economists have become kind of theory-centric in the late 20th century, AI was actually not so theory-centric in the mathematical sense. This is a sort of disciplinary history from Andy Barto, who sort of describes a history in which symbolic AI, the sort of world of good old-fashioned AI, he sees as not very mathematical, whereas something that branched off early on, which is this sort of statistical pattern classification, control theory, adaptive filters, he sort of assigns that to the sort of world of engineering and parameter estimation. And it, as you can see, it's kind of, it's separate from both symbolic AI and connectionism. And so the question is, like, how did that stuff on the left actually come back into AI, or come back into sort of the brand of AI that we're talking about now, which is like deep learning? And you know, he sort of explains that in the 80s, you know, sort of the period that he's writing about this, deep learning practitioners, you know, there weren't that many. It was like, you know, Jan LeCun, Jeff Hinton, people like that. They were just sort of like, you know, they were experimenting. They didn't really have a sort of formal statistical theory behind what they were doing. They were just kind of exploring and maybe post hoc coming up with a justification of why a particular architecture worked well. And so the question is kind of, again, you know, like how did decision theory come back into AI? And sort of my hypothesis so far is that Liam Batu, who is another French grad student in Paris at the same time as Jan LeCun, they worked on software. They sort of wrote like neural network simulators together. I think that, you know, he was able to basically draw on a different tradition of machine learning, which was that of Vladimir Vapnik, who in Russia was sort of inspired by pattern recognition in the 60s, and they kind of went way off in that direction. And Liam Batu sort of manages to bring it back in a kind of interesting way, where he sort of, you know, points out that a lot of machine learning does operate with reference to some sort of cost function, or, you know, cost or loss are sort of used interchangeably most of the time. And so the perceptron and k-means and these Cohonen maps could all be sort of seen as the same kind of thing in a sort of formal theoretical way. And I think that this is sort of the, you know, the beginning of this stuff sweeping back into modern AI. And so, you know, this is a video on the right of Jan LeCun's digit recognition and I think it's a demo from the early 1990s. And so he sort of redefines what Jan LeCun wrote in 1989 in the language of the loss function, in the language of the economic cost of delivering a letter to the wrong address, right? And so this is a sort of, I think, you know, an economist's way of looking at neural networks. And so you can see the guys who worked on the actual project is nice in the video. And so, you know, today we have, you know, textbooks on deep learning, and these textbooks are very, you know, unproblematically sort of talk about loss functions and even equate them to cost functions, loss functions, or error functions, or objective functions. It's all kind of the same thing for them. So in a way, you might say that, well, you know, maybe they aren't really incorporating this economic logic, and maybe maybe they're just, you know, using it as a sort of synonym for an error function, which is a more traditional sort of term. But I would say that in the case of generative adversarial networks, which are some of the most interesting architectures in like contemporary AI, you have an interesting situation where in this case, you have two models that are sort of competing against each other. The discriminator trying to distinguish between real and fake images, and the generator trying to learn how to make new images, new bitmaps that look like numbers. And what's neat about this whole situation is that, you know, the two models are kind of ignorant at the very beginning, and they sort of progressively learn from each other. And so I would think of this as actually quite social, but that's not really how the AI practitioners see it. Instead, they use the language of game theory to describe what's going on, right? So this is the sort of future of, like, I think of you know, social AI right now, in the sense that these architectures can be thought of as being kind of dyadic and interactional in some kind of way, because the language that's available to the researchers is from this, has come to be from this economic tradition. They use language like, you know, the discriminator and the generator play the following two-player minimax game with value function v, and so now there's, like, you know, profusion of papers trying to show that it reaches some sort of equilibrium, right? And so that, you know, the idea now that learning is not just this training process, but something that approaches a kind of equilibrium state is, you know, very much, you know, sort of amenable to the economists, and also, you know, I think, like, the ideology which will sort of, you know, continue to surround this research, you know, similar to the statistics research group, will be at this intersection of decision theory and game theory, and also be a perfect match for the upcoming wars in which these agents might one day participate. All right, thank you.